Hi and welcome everyone. In this video we are gonna discuss the RCD technical specifications. We are gonna look at the ABB catalog, and I obtained some pages from it so that you can see what does the technical specifications existing inside the catalog, so you can understand them well. So let's look at this one. So we have this model from ABB. 3-pole plus neutral RCPO. 3-pole plus neutral, you can see 3-phase and the neutral, as you can see here. Now, if you remember, what does RCPO mean? RCPO means a residual current device with overcurrent protection, meaning that it can act as an RCD unit plus a miniature circuit breaker, protection against overload and short circuit, and the protection against earth fault. So you can see here, residual current circuit breaker with overcurrent protection device are the ideal solution for installations where space is limited, reducing the space required by 50% compared to an RCCP plus MCP configuration. So you can see that instead of having a unit like this as an MCP, a miniature circuit breaker, plus an RCCP, which is a residual current circuit breaker, which is only used for earth fault, as we discussed in previous lessons. So instead of having one unit like this and another unit like this, now we combine. ABB gives this model that combines two in one device, which saves the space by 50%. I'm gonna show you another slide or another model in which we have RCD connected to an MCP, okay, which takes larger space. Now this makes it suitable both for new installation to save space in switch ports or for retrofitting existing installation by adding earth fault protection, current protection, in installation where this was not foreseen, without affecting the overall dimensions of the system and the placement of the whole system. What does this even mean? Now we have this one exist in a panel, and we can, let's say this is a conventional miniature circuit breaker. I can remove it and put this RCPO that does the two functions, the overload short circuit protection plus the new protection, which is earth fault protection, okay, without affecting the dimensions or the dimensions of the electrical panel. This is of course more expensive than the traditional one which you are gonna see. Now it has several types: AC, A, AB-R, and S. Now AC and A are types of RCDs that we discussed before, like AC, A, B, and F, that we talked about based on the load characteristics. Now S type, the difference between AC can be general type, which means it has no time delay. S means selective or has time delay, this type here. Now AB-R, this one is a special type of general type with a certain time delay. I'm gonna explain what does it do, or this is anti-disturbance circuit breaker or RCPO. I'm gonna explain what does this do in the end of this lesson. Now this one has a break capacity of 4.56 kiloampere. This is the rated break capacity, the maximum short circuit it can withstand. It has different sensitivity that we discussed in the previous lesson, 30 milliamperes, 100, 300, based on the model. Different sensitivity for different applications, which we already discussed in the previous lesson. Now, since this one acts as an RCCP and a miniature circuit breaker, this one MCP, we already know that it has different curves, B, C, D, and so on. This model here has B, C, and K tripping characteristics. Now K is simply part of D. D is from 10 to 20. K, if I remember, is from 10 to 14. I nominal. It can withstand this inrush current without tripping. We will see them in the next slides. Here we can see the tripping characteristic for all RCPOs. Now we have B and C according to this IEC standard, K according to this part of IEC. This is the rated current. We have RCCP plus MCP. MCP itself has type of curve C, B, C or K here, in addition to the nominal current or rated current that flows through the circuit breaker in normal conditions. So it has between ratings from 6 to 40 amperes to 41 to 40 for these types. Now you can see here we have thermal release and electromagnetic release. What does the difference between thermal and electromagnetic? Thermal is the mechanism for circuit breakers for overload condition that uses bimetallic strip that we talked about before, conditions. And electromagnetic release, this is a mechanism for short circuit conditions, short circuit. Now for thermal, here you can see it says that between 1.13 to 1.45 it will be between here more than 1 hour, and this one less than 1 hour to trip. This is the range which we are gonna see in the characteristics, or this representing the manufacturer tolerance. Same for the rest. Here we have a range which we are gonna see in the next slide. Now electromagnetic release, you can see that B from 3 to 5 times. Here you can see from 3 to 5 times hold the current surge and trip starting from 5I nominal. So it is the range for short circuit tripping. Here for 5 to 10 times for C type, K from 10 to 14 as I said before. Now let's see this in the next slide. Here we can see this is the characteristics for overload condition. This one, for overload condition, we have a tolerance here. It means that at 1.5 I nominal, it can trip starting from here, go all the way up till here. This is the range at which it can trip, from here to here. What you can see also here in the slide, conventional non-tripping current and conventional tripping current. This one is the non-tripping current and this one is the tripping current. So most likely it won't trip here, and here it must trip here at this one. So it has two values, one which will not trip and this one which it must trip. Another thing about this says tripping curve from cold state, meaning that these characteristics here, when the circuit breaker was shut down for more than an hour or circuit breaker has not been operated previously, been operated, meaning that the bimetallic strip are already in cold state, not in hot state. No current has been passed, so it will make it hot or convert it into hot state. Cold state means that no current had passed through this circuit breaker. Similarly, for characteristics of C and K, you can see there is a range 5 to 10, here from 10 to 15, here from 3 to 5 times. So this value, conventional non-tripping, this is the current at which it will hold for a very long time, more than 1 hour, without tripping. 1.45 means conventional tripping current. This means that it must trip in less than 1 hour when it reaches this amount of current. This is the meaning of these characteristics, which are more related to circuit breakers. Now let's look at this one here. Here we have another property which you can find here called let through energy, characteristics B and C. What does let through energy mean, or specific let through energy? This is simply I square T. This representing fault current, and T is the duration before the circuit breaker cuts the circuit. This one representing the amount of energy that goes through the equipment before the circuit breaker cuts the circuit. So why is this even important? Because it says that here at this value, 2.5 kilo ampere short circuit, we will have a let through current, let through energy of this amount here. Why do I care about this? Because my own equipment are designed to handle a certain let through energy. So every equipment has a rating for let through energy. So my circuit breaker will allow a certain value. So I should know that my equipment can withstand this value here. So specific let through energy is a measure of the thermal energy dissipated by the fault current as it passes through the circuit before the device can clear the fault. The primary function of this curve is to show how much limited thermal energy that the protected circuit and downstream equipment must withstand for a given short circuit current. Now let's look at this. So we said before that I have one unit that does two functions, RCPO, one unit which is RCD. We have an RCD which is the residual current unit and the miniature circuit breaker. Now here you can see that they are two separate units unlike the previous one. This part is RCD and this part is a miniature circuit breaker. RCD, MCP combined together, they are connected together like this. This one is on this one and we will have this. So what you can see here is that instead of having one unit that does the two functions, now we have two together. I have to install an MCP and an RCD unit which takes larger space in the system, unlike the previous one which was one unit to be removed and another one to be added which does two functions, an MCP and an RCCP. Now what you can see, this part here which is connected to this circuit breaker, when this one goes down or disconnected, it takes this handle here and also disconnected it. So these two are connected to each other. So when this one detects a leakage current, it will trip and takes this handle and trips it too, or trip the MCP too. So this range or these models are having DDA and MCP. This one refers to the DDA, refers to the RCD block according to ABB. They call it DDA. While this series doesn't offer space savings, it reduces installation time because these two are already combined in the manufacturer. They are not given separately, they are already combined by the manufacturer itself. Now we have also another property which is important, I peak. This one gives you the root mean square current of the short circuit and the corresponding I peak. This is also an important property for our equipment. Okay, now let's look at this time current characteristics according to IEC British standard, this one, and Australian or New Zealand standard 61008 and 61009. What does it refer to? Remember this table that I discussed before, domestic instantaneous type S, this one here, this one, similar to this one from ABB, similar to this table from British Standard or IEC. All of them are exactly the same. Let's explain this. First, it says that general non-time delay and another one with time delay. Instantaneous with time delay. Here the rated values for non-time delay, it has the rated available residual operating current. These are rating available 10 milliamperes, 30, 100, 300, up to 500. For delay from 100 to 500. Okay, you can see this in ABB. For I nominal current is for RCPO or the MCP part, any nominal current for them. Here for I differential or I residual, that's what I care about. For generic, you can see it starts from 10 up to 500, any value. However, for delay, more than 30, which starts from 100. More than 30, which starts from 100. You can see it starts from 100. So it says greater than 30 milliamperes. Now, tripping characteristics. At 1 of the nominal value, 2 of the nominal value, 5 times 500 amperes. Now, these are the one available by the standard, as we will see. So 1 time, you can see here 10 ampere, 1 I delta n is 10 amperes, 30, 100, 300, and so on. Similarly for delay. And this one here is double I delta n. You can see 10 became 20, 30 became 60, 100 became 200, and so on. Similarly for delay or S delay. Last one is for 5 times, 5 I delta n. 10 became 50, 30 became 100. What does this values mean? It means this one is the rated value. That's RCPO I delta n equal to 30 milliamperes. What does it want from me? It says the trip time at the same value, at 30 milliamperes, how long it will take to trip. At double the value, at 60 milliamperes, how long it will take to trip. At 5 times or more, how long it will take to trip. Now you can see that at one value, maximum value 300 millisecond, which is translated here 0.3 second. 0.3 second. This is from Schneider and this is from ABB. At double the value, 150 millisecond max, 0.15 second. 0.15 second. 40 millisecond, 0.04 or higher, 0.04. Lastly, for delay, you can see between 130 and 500. Same as here, from up to 0.5 maximum value, maximum operating time, which is 0.5 here. Second one from 60 millisecond to 200, maximum value 0.2 maximum. And for 5 times from 40 to 150, 40 to 150. Here maximum value 150. This one. So this is simply the translation of the code by ABB and Schneider. Now let's look at a time current characteristics for an RCPO, for generic, selective, and another type which we will discuss. Okay, let's look at this. First, this is the current characteristics, time current characteristics for instantaneous 30 milliamperes by ABB. An example. Another one, this is the time current characteristics for ABB also, but this time selective or S time with time delay. So this is a generic type or general time delay, type AC, instantaneous, and this is the selective, 30 milliamperes, 300 milliamperes. Great. We have another type which we will see in the next slide called APR, which is anti-disturbance RCD. This one is also 30 milliamperes and also instantaneous. However, you will see that this curve, this orange curve, is shifted upward from this one. Shifted. What does this mean? If you look at here at the operation time here and operation time here, you will see there is a time delay. Both of them are satisfying the standard requirements. However, this one has more delay than the instantaneous time. Now, what does these areas mean? So we see that between at one of the value, at nominal value, we have 30 milliamperes, 60 milliamperes, here 150 milliamperes, and higher. At one value, 0.3, this is the maximum time, which means 300 milliseconds. This is the maximum operating time. So you can see the operating range from 0 to 0.3 seconds here until the 30 this is the 30 milliamperes. 30 milliamperes from here to here. Great. Okay, this part here. Now double the value, it drops to 0.15 seconds, which is here. So you can see from here it goes like this. At 30, at higher than 30, it drops to 0.15 until double the value, like this. Then at 5 times, here, drops to 0.04, 0.04 here, like this. So it would be like this. So higher than double the value, drops to 0.04, goes from here to 0.04 until any other value like this. This region here is called the allowable operating region by the standard of IEC or any other standard that we have seen. Now what you can see is that my instantaneous type is within this blue region, and also my orange one, which has some delay, also in the operating region by the standard. So they satisfy the standard requirements. Similarly, for the selective, you can see here 0.13 to 0.15, here at 300 milliampere second, here starts from 0.13 to 0.5, okay, 0.13 to 0.5, this range here, 0.13, 0.5, this one. For the double the value between 0.06 and 0.2, 0.06 and 0.2, this range here, like this. Okay, so this is for this one, that's 300 millisecond, this range, but you will see that the blue region is also before it. See this one? Before it. Why is this? Because actually in reality, the RCD operates before the value it is operating at. For example, the 30 milliampere does not operate at a value of 30 milliampere. It actually can operate between 15 to 30 milliamperes before it. This is what we are gonna see in the tripping characteristics of RCDs in the next lesson. That's why we have a green area here. Sorry, a blue area here. Now similarly for between from here 0.04 to 0.15, 0.04 from here to 0.15, which is here, this range here, like this. Here 0.05 to 0.15, this is for the manufacturer itself. It changed it to 0.05. In the IEC it is 0.04 from here to here. Anyway, the blue line for selective for the RCPO is within the requirement by the standard. Summary for this, range of ABB RCDs has also AB-R anti-disturbance devices, which trip according to the limit times allowed by the standards for instantaneous RCDs. As you can see, this one is within the blue region for the standard. Why this function? This function has a slight tripping delay, about 10 milliseconds compared to the instantaneous standard ones. I'm gonna explain why in the next slide. Blue areas representing the permissible tripping time zones defined by the standard, as I just explained. Each RCD, as you can see, trips within the allowable range. Lastly, we are gonna discuss AB-R or anti-disturbance circuit breaker, or RCPO, residual current device, which is called also high immunity. So what does this even mean? Now we have a phenomena inside the transmission system or on our electrical system, in which we could have what we call a common mode voltage surge, or an increase in voltage with respect to the ground for line and neutral. This is called common mode surge. Line with respect to the ground, V increased, neutral with respect to the ground also increased. Common mode. Another one called the differential mode, which is the over voltage happening between line to neutral. For example, line increased relative to the neutral. Okay, so this is the meaning of this. Now what I'm gonna discuss, or what I care about now, is common mode surge, in which line increased with respect to ground, neutral increased with respect to the ground. Why does this even happen? Now we know that in some cases in our electrical power system, we have over voltage surge due to transient actions or transient switching action. So when we turn on and off a supply, we can have a surge like this one you can see here. See this surge, that the voltage will go to a large value and then it starts to go down. Now this waveform happens for switching action in power system, switching loads on and off, starting of motors, switching off loads, and so on. Another reason for this is lightning strikes, which can have this voltage waveform. Now what is the problem of this? Well, actually what you will find is that, for example, for lightning strikes hitting the ground, this lightning strike has a very high current and also very large change in this current. We know that the lightning strike current is like this, goes very large and then drops down to zero for a lightning strike. Now this one has a very large di by dt. This means that we know that current has also that magnetic field flux, and since di by dt is large, the rate of change of current is large, the d phi by dt will also be large, rate of change of magnetic field is large. Now why would I care about this? Because induced voltage is equal to negative n d phi by dt, meaning that any closed cables or conductors like phases and neutral will be subjected to a large induced EMF. So there will be a large induced EMF on these conductors with respect to the ground. So there will be an induced EMF with respect to the ground. This is what we call a common mode current surge or voltage surge. So why would I care about this? Because let's say we have some electronic equipment that, like computers, that has input filters. See this filter between phase, ground, between neutral and ground. This filters has a capacitance C. Now what is the problem here? The problem is that this voltage will be looking like this. This induced voltage, di, it changes, the rate of change of voltage is very quickly, or voltage surge like this. So why would I care about this again? Because this one has a large frequency. Now, since it has a large frequency, we know that the XC here, XC is equal to 1 over omega C. When the frequency is high, XC drops down. So V, which is induced EMF, over XC will be a large value, right? So what is the problem? The problem is that this will be equal to, this is a current equal to E over XC. So there will be a leakage current going like this through these equipment, through these filter capacitors, like this. Go like this to the ground. Go like this to the ground, like this. So what is the problem? The problem is that RCD will detect these currents as leakage current despite being in a very short time. However, due to this very large amount of current, this RCD will operate. So how can we solve this issue? We have what we call the anti-disturbance RCDs, which have a little bit time delay, 10 millisecond. This 10 millisecond allows it to not operate in case if we have these over voltages. So equipment like computers, inverters, and so on have capacitive input filters connected between phases and ground, neutral and ground. Operation overvolt caused by inserting or removing of fluids, starting of motors, and so on. Overvolts can be of atmospheric origin caused by direct or indirect discharge on the electrical line. For example, lightning strike magnetic field cause induced EMF, or when a transmission or lightning hits the transmission system. This common mode voltage surge, because both of them will have large voltage compared to with respect to the ground, will lead to a common mode current. Each of them will have current going to the ground due to the common mode of capacitance of cables and filters. So filters and these cables here has also a capacitance with respect to the ground. This is the combined value of them. So this current will lead seen by RCD and can lead to a tripping of the circuit. So we have type A-SI super immunized by Schneider Electric. So A-SI is same as AB-R or anti-disturbance ABB. Both of them are used for protection against disturbances. Thank you for watching this lesson in our course for electrical design. If you would like to learn how to design electrical systems from scratch, we have a large course on electrical design in which you are gonna design electrical systems in AutoCAD, Dialux, Excel, ETA. You will also learn how to select circuit breakers, cables according to MEC and IEC standards. We are gonna go step by step in AutoCAD and how to draw the lighting circuits. We will also learn how to do the lightning protection systems in addition to SPD or surge protective device. This is a large course, as you can see here, which is gonna help you in becoming a professional electrical design engineer. Thank you and see you in our course for electrical design.